All right. I don't know if that's okay. All right. So I don't think I can. Yep. I think that's just something. So all right, we're going to talk about the very last section, section 12.3, right, in the book. But before we do, I wanted to do a quick little review. So just think about these questions as warm-up questions. And I think I already gave you this heads up. Just another heads up. So we're going to do a hypothesis test and a confidence interval today, like that go together. You know how every hypothesis test has a confidence interval that goes with it? So we're going to do like a pair of those today. I'm going to be dead honest with you. This is really annoying. This is definitely our most complex. There's like a lot to this. Some of it's going to be like new. This is like a tricky one, you know? But the good news for you, because this is so tricky, is that you'll kind of see what I mean as we go through. But on the AP exam, number one, this concept is not very heavily weighted, but also number two, the way that they ask the questions are, you know how like in the last couple chapters, it'll just give you some information and say like, do a hypothesis test. You know, it's like when they ask you these questions, it's typically not just information, do a hypothesis test. It'll typically be just like, check the conditions, or like it'll give you, basically you aren't going to have to do everything from start to finish. Do you get what I'm saying? For this, because you'll see what I mean. I'll give you lots of practice problems and you'll see exactly what I'm talking about. So it'll make more sense later. But it's gonna, especially in the beginning, it's gonna feel a little overwhelming. There's a lot, okay? And just keep in mind that it's a lot, but at the same time, the questions are typically, you're not going to be like, just do a hypothesis test, start to finish. We'll get there. Don't worry. You'll be good. All right. So think about these questions real fast. You can talk about them if you want to, write them down, whatever. I'll give you a minute or two.
It's the distribution of all the possible
I was thinking variability. Simply variability, which is what like something happens changes. You're not gonna get because because of like data is like it would seem like it's like significant amount like you don't it would find chance right?
Well, that concept's based on sample variability, but it's the idea that a given sample of any population I take, all of them will be different. None of them are going to be perfect, and none of them are going to be perfect. So there's always going to be a variability between each and every one sample, and a sampling distribution kind of gives a graph of that variability by presenting each possible value, whether that's range, whether that's mean. Put that up there in that graph. And the relationship is that sampling variability is kind of sort of graphed by sort of samples.
All right, let's talk. What is sampling variability? What's sampling variability? What did Nora say?
It said that every sample of a population is going to be different. So it's just that idea that they're not all going to be the same.
Yeah. When you sample from a population, if you're not doing a census, right, you're taking a random sample. So every time you take a sample, if you take the sample mean, or if you take the sample standard deviation, or the sample median, whatever statistic you're measuring is going to be different with every single sample, even if the population value is always the same, right? Okay, so that's sampling variability. What is a sampling distribution?
You can take multiple samples and you can see where about their centers and spreads are going to be.
Yeah, so if you take lots and lots of samples, the important part is those samples all have to be the
same size.
Same size. Do you guys remember that?
Yeah.
So, well, now you do. So with the sampling distribution, you're taking samples from the same population, and each sample is the same size. So like a random sample of size 50 or whatever, you know? And you're gonna sample over and over and over and over. And I'm now gonna kind of answer number 3 as well, right? But if I think about sampling variability, when I sample over and over and over, sampling variability tells me that each of those, let's talk about something different. You talk about like mean and proportion a lot, right? Let's talk about median. If I want to find the sampling distribution of the median of a certain set of data or whatever, I would take samples of size 50 over and over and over and take the median of each of those samples, right? And if I take all possible samples of size 50 and all the medians of all those possible samples, that would be your sampling distribution, right? And I heard Reardon say something about like, where would all those medians be centered? So they would be all different values, but what?
Near the population center.
Yeah, they would be centered around the population center. And what shape do you think that sampling distribution would be?
Approximately.
A lot of times it's approximately normal, right? So we've talked a lot about like sampling distributions being approximately normal. If various conditions are being met, right? Okay, so that was our quick review of like chapter, I think that's like chapter 7, right? So,
Spend a lot of time staring at the text.
I guess I can't click this like this with this thing running. All right, hold on. All right, so we are going to talk about more about linear regression. So we're going to do
Regression is the worst possible thing for
no.
Yeah.
All right, guys, so we're gonna do a confidence interval and a hypothesis test for the slope of a regression line. All right? Now listen, before we get into any of this, let me ask you this question. So linear regression, we have like 2 variables, right? A person's like height and a person's weight or something like that, right? Or a person's height and their shoe size, or a person's age and their height, or, you know, SAT score and IQ, right? And you measure each of those variables on all of the individuals, correct? So let's think about something like maybe a person's height versus their IQ. And let's assume that we're only talking about like people 18 and older, okay? So we're getting rid of the like adolescence type, you know, thing of like growing, okay? So we're only talking about adults. If I were to look at a person's height versus IQ, and I were to take like a really large SRS from all like US citizens, what do you think that scatter plot would look like? All over the place, right? Because the correlation would be close to 0 because these 2 things are not really, they're not correlated, right? So we would have like a lot of random scatter. I love this review that you guys are doing. So our R value would be like, not 0, but it would be somewhere like close to 0, right? If I were to still, even though it wouldn't really be very meaningful, but if I were to come up with the least squares regression line from a set of data that looked like this, what would the regression line look like?
Close to flat.
Yeah, close to.
Yeah, it would look close to flat. So like, is the slope positive? Is the slope negative? Where's the y-intercept? Somewhere like in the middle, you know what I mean? So it definitely wouldn't be flat, right? Because nothing is perfect. It could be flat, but it would be something like this. You know what I mean? So the equation of the line would have whatever y-intercept, but the important part is that the slope would be 0, right? You with me? So in other words, if I have two variables that are unrelated, uncorrelated, if one doesn't affect the other, theoretically the slope between the regression line between the two variables should be close to 0. You with me? On the other hand, if I have two variables that, let's say, like height and shoe size, or like maybe height and weight, something like that, okay? So what do you want to do? Let's do height and weight. So height and weight, do you think these two variables are correlated? Is it perfect? It's not perfect, but generally, as people are taller, they weigh more, right? So that doesn't mean that we're going to have like a perfect linear correlation. You know what I mean? We're going to have some scatter. So you're going to have some tall people that weigh like less than average. You're going to have some short people that weigh more than average. You know what I'm saying? But generally, you're going to have a relationship, a positive relationship. Your R value is going to be what kind of a number? A positive number. And if you were to do a least squares regression, the linear regression line, the slope would be positive, right? Now, in this section, we're not really going to care about the y-intercept, because the y-intercept can be anything. We really care, so we're kind of like answering the question, is there a relationship between the two variables? Do you understand? So if there is a relationship, then the slope of the regression line will be positive, or it could be negative. Give me two, off the top of my head, why can't I think? But give me two variables that would be like negatively correlated.
Amount of money, if you didn't have a job, amount of money, and then like months to die.
Oh, I love it. Okay, perfect. If you didn't get a job, good. Those two things. Oh, I love that. I love that. So those two variables, the things you guys are giving me, are correlated. Do you know what I'm saying? The R value would be negative, the slope would be negative. But again, does it matter what the y-intercept is? It doesn't. The y-intercept doesn't really tell us about the relationship. It's the slope that does. You with me? Okay. So in this section in the book, 12.3, it's all about the slope. So here we go. Are you ready? You are. It's 71. 71. All right, ready? Listen. Look. Read this carefully. Read this very carefully. This is a scatter plot of the duration and interval between eruptions of Old Faithful for all. So this is a population. All 263 eruptions in a single month. So this is just over the course of 1 month, right? But this is a population. So notice the population least squares regression line is shown in blue. So all of the stuff that we did in chapter, was that chapter 2? With least squares regression, 2 or 3, I forget, I'm sorry, I'm so bad. But whatever chapter we did least squares regression, we always used like y what? Y hat, because it was
Expected.
it was like an expected, it was a prediction, right? It wasn't a population. So we had like a sample. In this case, we have a population, got it? So the red dots, those are all the eruptions. Tell me, do you think there's a relationship between the duration and the interval until the next eruption? Yeah, the relationship is as the duration goes up, the interval until the next eruption also goes up. You know what I'm saying? Okay. Do you notice that there's also kind of like two clusters, like here and here? And there's, yeah, so we wouldn't really say it's bimodal, but we would say there's clusters. When we have like a scatter plot, that's I like that. But in a scatter plot, we more say that they're clusters. Anyway, so if I were to do a least squares regression line the same way on the calculator, whatever that we did before, notice my equation, I don't use y hat, I use mu sub y, because this is the population average number of all the y's. Got it? So my population linear regression equation looks like that. Questions? All right. So look, let's talk about notation. Just like all throughout the year, when we have data that comes from a sample, we use like X bar or like S for standard deviation. If it comes from a population, we use like mu, right? Sigma. So generally, population is like the Greek letters, sample is like the, what do we call our letters? English letters, whatever. What are they called? Normal letters. Yeah. Our alphabet that we're used to. All right, so look, a regression line calculated from every value, in the population looks like this. So it's mu sub y is equal to alpha instead of what letter do you think? A, yeah, plus that's a beta x. So a beta looks like a B with like a little tail. So listen, here's the first confusing part. This alpha is not the same value that we're used to in terms of like the alpha value, like the cutoff score in our hypothesis test. Do you understand? Let's make that very clear. There are two different like total meanings, all right? So that's your population regression equation. In chapter 2 or 3, whatever, our regression equation from a sample of data was y hat. So y hat estimated mu sub y. A estimates alpha, and then the letter B estimates beta. Got it? So beta is the slope, alpha is the y-intercept. Sorry. Question?
Yeah. Since it's like a hypothesis testing, are we still going to be using
An alpha value, yeah. But don't, here. Remember, when we do a hypothesis test, do we have population values? No, so we don't have these. We're saying we're going to use the letters A and B. Do you know what I mean? In your hypothesis test, you're not going to use alpha, you know? Nora, did you have another question?
So why is it a mean then instead of just a y value?
Good question. So we're going to talk about that a little bit more as we go through. So y hat is, let me go back, hold on. Look at this regression equation, or look at the regression line in it, okay? So the whole idea of a regression line is that it's the average y value at a given x. So let's say, like, you know what I'm saying? Let's say x is 4. If x is 4, your values, you know, your y values go anywhere from like, what is that, like 100 to like 75 or something like that. You know what I mean? So the least squares regression line is the average of those y's at that value.
Okay.
Make sense? And so y hat really means, like, remember we said the predicted or on average?
Yeah.
You know, so this is like a population. Got it? Good questions, guys. Okay, anything else so far? All right, here we go. I'm laughing because the fun is about to begin. So if I were to take samples from that population, sampling variability tells me all those samples would look a little different, right? So I'm going to take different SRSs of 15 of each of those, you know, red points. Got it? So that's what one SRS looks like. The blue line is the population regression line. Is the sample like regression line going to be the same as that? No. So notice, look at my equation here. Do you see like y hat and then mu sub y? They're a little bit different. Now my y-intercept is 44. Down here it was 33. My slope is 10. Down here it was like 13.29. Got it? But does think about like the shape, you know, look at like just the red dots. Is that kind of representative of the population? Like you kind of still see like the two clusters at the end. Here's a different SRS, right? My equation is different, isn't it? Here's a different SRS of size 15. My equation is different. So remember, there's different hypothesis tests for y-intercept as well that we don't learn, right? But we're only focused on slope. Look at this slope. Focus on the slopes. 10, 12.5, 15.7. They're kind of close to 13.29. Some are a little bit above, some are a little bit below. Does that make sense that that would happen? Because that's called what, guys? Sampling variability, right? You with me? Okay, so that's kind of, I think what this says here. All right, so the pattern, if we were to sample over and over and over, all possible samples of size 15, the pattern of all of those slopes would make up the sampling distribution for the slope. So we know, you guys told me before, the sampling distribution would be centered around the population value. We knew that the population value was 13.29, right? Because we had that regression line for the whole population, so that's this blue line here. So in other words, these green like dots that kind of run together, but the green dots are individual slopes from all the different possible samples, and then we did like a regression of each of those. Again, the important part, each sample had size 15. Got it? That's a sampling distribution. All right. So if we think about the shape, what does the shape look like? Approximately normal, right? What does the center? Where's the center? It's close to, in fact, it's going to be exactly 13.29. Remember the terminology, an unbiased estimator? Unbiased means it's centered around where it should be. That's what unbiased means. So it's unbiased because it's centered around the population value. Got it? So variability. Doesn't that formula look fun? So the variability, you don't have to memorize this. Actually, get your things out, your formula sheet.
My question is it
Go ahead.
going to be like interpretation on the formula sheet, or is it like it's actually going to show the formula?
Hold on, what?
Is it going to be like when you say it's like on the formula sheet and I'm looking at it, it's just words, or is it going to be like?
No. It's going to give you the formulas. Here, flip to the second page. Second page of your formula sheet. And now at the top you have proportions, and then in the middle you have means, and then you probably never get most all the way down at the bottom. Here is your stuff, your formulas for slope. So do you see this formula right here? This is what I'm talking about, like right here. Do you see it kind of like in the middle? So it's called sigma sub b, because remember b is the slope of a regression line. So it's the variability or the standard deviation of all the slopes is going to be equal to, there's a lot of sigmas. So the sigma at the top, and this part you do need to know. This part you need to know, but the sigma at the top is the standard deviation of the residuals. Do you remember? And we called that S in chapter 2 or 3, whatever it was. The standard deviation of all the residuals, remember, was the average distance of the residuals from the regression line. Do you remember that? So that was S in, earlier in the year because it was from a sample. Now because it's from a population, we're going to call that sigma. So the top sigma is the standard deviation of the residuals. And then there's a sigma again at the bottom. Do you say sigma of X? So the sigma of X, I think, is a little easier to remember because it's the standard deviation of all the X's. And if you go back, I can go back for a second, but look at your two variables. Hold on. My two variables were duration and interval until the next eruption. Do you know what I'm saying? So sigma sub X literally means sigma of the X's. Do you understand? So it's the standard deviation of the disruptions. Question so far?
Is the X going to be the slope values or the actual values in the same?
Uh-oh, wait, hold on. Wait, ask that question again. I'm sorry, let me listen.
Is that X going to be like the slope values, or is that going to be the X's in the sample?
From the sample. Yeah, this is like sigma sub X. It's the standard deviation of all the X values. You know what I mean? So if you were to ignore the fact that this is like, X comma Y, like if you have a bunch of points like 10 comma 7, 5 comma 3, ignore the fact that there's an X and a Y that go together. If you just look at the X's and you find the standard deviation of that, that's that value. Do you get it?
Yeah.
And then divided by the square root of n, where n is the number of points that you have. Got it? Okay. So that's that formula. In summary, this is what we have. So the sampling distribution for a slope is approximately normally distributed. The mean of the sampling distribution, mu sub b, is equal to beta. Remember, beta is the population slope. And then the standard deviation is that fun formula. Cool? Okay. Here we go. Conditions. So listen. Hold on. Let me actually, before I show you this. Listen. You're gonna see when we get to these problems, you're gonna see they're kind of nice about the way they ask the questions. So just bear with me. Ready? Let's go back. Remember we talked before about, like, if I focus on when x is equal to 4 only, the values for y go from, like, what do we say, 75 to like 100, something like that, right? So if I focus just on individual x values, you with me? This distribution of these y values in the y direction, so up or down, where are they centered? They're centered at the line. They're centered in the middle, right? So the first condition, part of the conditions, is that if I take all those points with this x value, they're not all going to be the same, even in the population, right? But they're going to be normally distributed around the line this way. So most of the y values, remember we're focusing just on y values. Do you get it? Most of the y values are going to be close to the line, and then they start to, like, spread out a little bit, but you're not going to have as many y values, like, further away from the line. You know what I mean? So, like, in other words, the scatter is happening, like, closest to the line. Do you know what I mean? So for each individual x value, the y values go from, like, here to here. You know what I mean? And if I look, that distance down here looks pretty close to this distance up here. You know what I mean? And even here in the center where I don't have as much data, like, there's still some spread along in the y direction. So the condition is that spread happens in a normal distribution. All right, let me go back.
I have a question.
Yeah, go ahead.
No, like, you know the next slide.
Yeah, the one where the condition, hold on, do you have a question? Should I stay here?
So,
And then I'll answer all.
so is it normally distributed, like, for a given value of x?
For a
Like,
given
it has to
value
be
of
the
x.
same- It's not like from x to x, it's just like all the points in the same x
Yep.
value?
So for a given value of x, the values of y are approximately normally distributed around the linear regression line. And remember, the linear regression line is in the middle. Any other question?
If the x only has one value, like, if you're...
Remember, this is for the population. So you still could only have one value of x in the population. But go ahead, ask your question.
Like, does the approximately normal stuff, would that still work even if you only have two or more values on the thing?
Okay, so good question. Theoretically, I mean, if you only have one value, you only have one value. You can't say it's only distributed. So a lot of this is kind of like theoretical. You know what I'm saying? In that, yeah, look at these points that I pointed here. Are these all 4? Is the x exactly equal to 4? No, you know what I mean? So it is kind of like, in that sense, like, this is like theoretical. This is like the theoretical condition. You get what I mean? Here, let me show you what would be bad, okay? Here's what would be bad. If I had, like, let's say the red points, and then I added these other red points in here, then do I really even have, like, a linear relationship anymore? No. And part of the reason why is because these points for these like X values in here are not normally distributed. They're not close to the line. Do you get what I'm saying? Yeah.
Yeah, that was nice, but I just, you wouldn't say like it weekends.
It weakens the relationship, definitely, because they did not follow the pattern. You know what I mean? And therefore, one of the most important condition that we'll get to is that the relationship has to be approximately linear. You have to look at the scatter plot to begin with. If the scatter plot's not linear, remember the one we did in the on the warm-up slide with like IQ versus height? Why would you do if the relationship's not linear to begin with, remember we said you should never do a regression. You know what I'm saying? Okay, let me go back. Phil, did you still have a question?
Yeah.
Go ahead.
I was gonna ask about the 3D.
Yes. Yeah, here we go. Hold on.
I think are you on Florida?
Yeah, hold on. I'm getting to it.
I was confused.
There we go. This?
So is that representing the sample, like the cluster that you're saying, like, so that's the approximately normal of the sample?
Yeah. So this is almost like a 3D model.
Yes, 3D.
So here's X, here's Y. Remember, we had like those two, like clusters, and then there was some stuff in the middle. But we're saying for each X value, the Y values go from like here to here, here to here, here to here. So they're not the same Y values, but the distance between the max and min should be about the same. And they're all like, you have like if you could put the dots on top of each other, like stack them up, they would be approximately equal. Does that kind of make sense? Okay, this is definitely confusing. Yeah. Go ahead. All right. So let's talk about the conditions in detail. There's 1, 2, 3, 4, 5 of them. So 5 of conditions. All right. I'm going to go out of order, and then I'm going to tell you why these are in this. Let me tell you first, actually. They're in this order because in order to remember them, look, it's linear without the A. L-I-N-E-R. Like Fido's socks, right? So the condition, liner, whatever. Yeah, I like it. So the conditions spell liner. Got it? All right, so I'm going to go not in that order because I think it makes more sense. But first condition, I'm going to start at the bottom. The data have to come from an SRS. The data have to be representative of the population. You know what I'm saying? Or if you did a randomized, if you did an experiment, your 2 groups had to be randomly allocated. Got it? So same as before, SRS or random allocation. You with me? Okay. Independence. So now I'm jumping up to the I. How do we check independence a lot? 10% condition. If your data, so remember, random, we have 2 options for the random condition. It either came from an SRS or it was randomized from an experiment. You with me? So if it came from an SRS, we're going to check the 10% condition. If it came from a randomized experiment, you don't check the 10% condition. Remember?
Yeah.
Just like before, yeah.
We just say they're not sampling without replacement.
Yep. So because we did a randomized experiment, we're going to assume independence. And you can assume independence because they were randomly allocated. That's why you can assume independence. All right. So those are our first 2 conditions. The next one I'll talk about is the L, linear. The relationship has to be linear to begin with. So you have to make a scatter plot of X versus Y. And listen, when I say make a scatter plot, remember I told you they make the questions a little bit easier. Most of the time, you're not going to be entering data into the calculator. They'll give you a scatter plot, and you just look at it and say it's linear. So you either look at a scatter plot and say it's linear, or do you remember looking at residual plots?
Yeah.
How do we know if I just look at a residual plot, so like the X value would be here and the residual value would be here, and then there was always like that line at Y equals 0, how do we know from the residual plot if the relationship is linear? It's randomly scattered. Oh God, you guys are so good. So look, if so in order to prove the L condition, you're going to either look at the scatter plot and say it looks linear, or you're going to look at a residual plot and say that the residual plot looks good. Got it? Okay. So now let's go down to the N. Let's do N. So normal. So this is the one that we were just talking about before. So basically for each value of X, the Y values should be approximately normal around the, the linear regression value on that line. I'll just stop there. So that's the condition, and we'll talk about how you check it in a second. And then the other thing, E, equals standard deviation, kind of going along that same thing. So not only should they be normally distributed, but remember I said, like, I used my finger to check, like, look, where was it? Like the distance between, like, the max Y and the min Y is about the same in all of these. Do you know what I mean? So that's that E. So the Y value should be approximately normally distributed, but they should be approximately normally distributed with a similar variability. You with me? Okay. So that's linear, or what did we say? Liner. Sorry, liner. Yeah.
So, I know you put in like this order for liner.
Yeah. You can put it in whatever order you want to put it in on your
Is
paper.
there like on the other conditions that you put in order, like order we do when we're solving?
You don't even need
Is
to.
there like that where it's like you want to check random?
No. Yeah. Even on the other conditions, it doesn't have to really be in a specific order. Yeah. It can be whatever order you want it to be in as long as everything's there. Do you know what I'm saying? All right. Questions on conditions? Okay. Honestly, the conditions I think are the hardest part. So I think we're through the worst. So let's just practice. No, we're at 22. 22. All right. Let's check the some of these conditions. So linear. Remember we said we look at the scatter plot over on the left. Is the linear condition met? Yes. But over on the right, this is a different set of data. On the right, I don't have a scatter plot. I have a residual plot. Is the condition met? No. You good? That should be pretty easy. Okay. Independence. We already talked about this. So either if it's an SRS 10% condition, or if it's an experiment, the groups have to be readily allocated. Good? Got it. All right. Normal. So this one's definitely going to be the most difficult, okay? So what you have to do, so remember the condition itself says for each X value, the corresponding Y value should be approximately normal. But here's the thing. In order, Amanda, to your earlier point, in order to get normality, you have to have a bunch of points, right? When you find an SRS, your whole sample size is only going to be maybe 30, 40, or even if it's like 100. How many points are you going to have at each X value? A lot or a little? A little. Do you know what I'm saying? So, Amanda, this is exactly what you were getting at before. You really can't determine for each X value, do you have normality? You know what I'm saying? So what you do is you determine, do I have normality on the whole? But it's normality of the residuals. So you have to look at the residuals, because remember, residuals is the distance in the Y direction from the line. And that's exactly like what we're talking about, right? So what you're going to do is you're going to look at a histogram, a dot plot, a stem plot, a box plot, or a normal probability plot of the residuals. You want the residuals to be approximately normal. So I would maybe just like jot that down. So we want the residuals need to be approximately normal. So that's really what you're going to check. You're going to check to see, or I should, hold on, let me write, all the residuals like together are going to be approximately normal. Make sense? Yeah.
So would you just make a residual list on your, like, in your
Remember-
stat plot thing?
I'm gonna stop you right there. Yes, but no. Remember they make it easy for you to check? I'll show you. Like, yes, remember I said you're not gonna be doing this from start to finish. If you did have to do it from start to finish, that's what you would do. But I'll show you what you're actually gonna do.
Okay.
All right, ready? Equal standard deviation. So that's basically, again, looking at the residuals. The residuals for each value of x should be equally scattered. So look over on the left. This is an example of a good residual plot. So a lot of this is looking at the residual plot. So residual plot is randomly scattered. Over here on the right, if you think all the way back to when we first did residual plots, do you remember that? And I know. We said that when you have data that like is like that cone shape or whatever, like a triangle, you know what I'm saying? How it like kind of spreads out. So the variability in the low x values is way less than the variability on the higher x values. Do you see that? That's bad. So we want variability to be equal for any x value. Do you kind of understand what that's saying? So this is bad, the condition's not met, this is good. Got it? Okay. What are we missing? Random, we talked about that. SRS or need to be randomly allocated. And then that's it. All right, ready? We're gonna go through an example. So remember I said you're not going to really do problems from start to finish, meaning they're not going to really give you a list of x and y's, and you have to make the graphs. Most of the time they're going to give you graphs, and then you need to just have the conditions. Number one, you have to have them memorized, and you have to know how to check them. Okay? So let's look. Ready? Take a minute and read this. It was a fun experiment. So if you look at the first graph over on the left, what is this? Like, is it a residual plot? Is it a scatter plot? What is it? A scatter plot, but it looks kind of weird. Why does it look kind of weird?
Because the drop heights are
Yeah, the drop heights are discrete, right? There's only like 4 given drop heights. You know what I mean? Oh, 5. Sorry. Thank you. I was like, why is it spaced that way? Yeah, like you can't drop from like 325, right? You know what I'm saying? But I'm getting ahead of myself. Is the relationship still linear, do you think?
Yeah.
As x increases, does y tend to increase as well? Yeah, right? So anyway, this is your scatter plot. In the middle, it's your residual plot. And then what's on the far right? It's the residuals. So it's a histogram of the residual values. Got it? So before you do anything, I would always like look at the graphs and make sure you know exactly what they're giving you, because sometimes they'll give you different types of graphs and you have to like know what to use, you know? Phil.
Is it better for the x value to be discrete instead of continuous for this type of stuff? Because like in this case, it's easier to tell.
Yeah. When the x values don't have to be like specific values like this, it's always like easier to tell. So this is probably going to be harder to tell conditions than like normal. Yeah, good point. All right, so ready? We're going to check the conditions. Remember, liner, right? So L stands for linear. So the scatter plot shows a clear linear form, and there's no leftover curved pattern in the residual plot. So really, you don't need both of these things. You don't need both parts. You could just say the scatter plot of x versus y, drop height versus flight time, is approximately linear. That's condition 1. Got it? All right. But remember, we said we could check a residual plot as well. It looks like, again, you have to kind of ignore the fact that there's only like incremental x values, but it looks approximately good, like a good scatter there too. All right, independence. Was this an SRS? Let me go back. it was an experiment, they were divided, they were randomly allocated, right? It's somewhere, in a random order, right? So because they were dropped in a random order, we can assume that you have independence. Knowing the result of one observation shouldn't help us predict the value of another. Got it? If you check the 10% condition, are you going to lose credit? Yes. You cannot check the 10% condition.
Wait, why is that?
It's not an SRS. Remember, 10% condition is only for an SRS. Always, always, always. And that is a big way, not that they try and trick you, but that's a big way that people lose credit, you know? Okay, so normal. Remember, we look at the normality of the what? We want what to be normal? Residuals, right? How can we tell that? The histogram. Does the histogram of the residuals look approximately normal? It does. We're not going to go check the 68, 95, 99.7 rule. We're just going to say it looks like it could be normal. Got it? Equals standard deviation. Remember what that means. You check the residual plot, and for each x value, does it look like the y values are approximately like scattered throughout? Yeah. And look, they note here, I think, that there was more variability for the helicopters that were dropped at this height, but I don't even think you need to note that. All right. And then R, we said R is the random condition. It wasn't an SRS. They were randomly assigned to drop heights. Good? So those are your conditions. Questions? I know. Hold on. We're almost done.
I could imagine watching this video.
You're like watching right now, like.
Yeah. Go ahead. So listen, that was just conditions. Now we have, here's a good thing to note for this section and also earlier in the year. Remember, nothing is perfect. No residual plot is truly randomly scattered. No, scatter plot has like a perfect correlation. Nothing is perfect, right? Okay, so do you want to take like a little pause?
Yeah.
Okay, I can pause this. We'll take a little pause. All right, ready? I unpause. Ready? Okay, so I'm going to kind of breeze through this because we kind of already talked about this. So mu sub y equals alpha plus beta x. That's the population. That's the population. Those are the population values for the least squares regression line. Y hat is equal to a plus bx if your data comes from a sample. A estimates alpha, B estimates beta, S estimates sigma. What's sigma again? What's S? Standard deviation of the residuals. The standard deviation of the residuals. Got it?
Yeah, and that's really not on our formula sheet.
Right.
I saw it in the textbook and I was saying, like,
You don't need to know that formula.
yeah, because
If it's not on the formula sheet, you don't need to know it. Yeah. So look, just as a reminder, normal, the center of the sampling distribution is normally distributed. The center's at the population slope, and the standard deviation is that terrible thing, right? Now here's, wait, where?
The standard error.
Yeah, right there. That's a date.
Yeah, that's a B, because it's the standard deviation of the slope. That's if you have the population, or if you have the population values, right? Do we have the population values? No. So just like before, we can't call it the standard deviation, we call it the standard error, and we use the sample values to estimate the population values. So instead of sigma, we use S. And remember, sigma and S, again, are the standard deviation of the residuals. So this is S. This S right here is the standard deviation of the residuals from the sample. Remember, S of X, or sigma sub X, is the standard deviation of all the X values. N is the sample size, but because we don't have the population, remember degrees of freedom? Okay. So that's called our standard error formula. Questions? Phil, did you have a question?
So like, you know, like on the formula sheet, it says like that, but then it says where that equals the more, like the summation notation. Am I expected to be able to do this summation notation, like square root thing?
It's just defining the variables.
No.
Like, I want to do
Listen,
that ever?
you are never going to have to actually really use this formula. You should understand what each of the parts is, but you are never going to have to really actually use it. All right, look. Interpretation. Remember, standard deviation is on average how far are you from the mean, right? And standard error is the standard deviation when we use estimates from the sample. So the standard error of the slope is interpreted as how far is the sample slopes, or how far are the sample slopes typically from the mean, or in other words, from the actual true population slope. That you need to know. Remember we said like interpretations? Good? Okay. So here's what, remember like these things? When you have like the output, this is really how you're going to do like your confidence intervals and your test. So we have that helicopter data. We had 70 paper helicopters dropped from various heights, oh my God. And then if we were to do a least squares regression on that data, this is what we would come up with. Good? All right, so quick recap. What is the estimate for alpha? Here's your formula. I put it over here. Remember, alpha is the y-intercept. So what's the estimate for alpha? It's a constant. It's that negative 0.03, right? Interpret that value. What's a y-intercept tell you? Yeah, where the line starts. So in the context of this problem, on average, yeah, because it's if the helicopter were dropped from a height of 0, it is negative, but it's pretty close to 0, right? It's an average. So here's your interpretation for your y-intercept, which is A, good. All right, what's the estimate for beta? Beta is the slope. So the estimate for beta is what? 0.0057, right? So what's the interpretation of slope? Remember, I always think like rise over run. Change in y over change in x. Yeah. For each increase of 1 centimeter in drop height, the average flight time increases by that many seconds. Got it? Sigma. Sigma is what? The standard deviation of the residuals. So do you remember on here where that is?
I mean, that's the S.
It is the F. Yeah, so it's the S. So S is that 0.16 number. Remember, that's the standard deviation of the residuals. That's the average size of the residuals. Because remember, residuals can be positive or negative. So it's the average distance from 0. So the actual flight times, and remember, residuals in the y direction. So y is the flight times. Questions?
What's the interpretation of it?
Right here. So it's on average, how far are you in the y direction? So your y was the flight time, right? So the average flight time was, the average change in flight time is 0.168. Make sense? Or the average distance, sorry. So standard error of the slope, ready? That's that crazy formula. Standard error of the slope is the sigma over sigma x divided by root n of the, right? Guess what? Remember I told you really aren't going to have to use the formula? And remember earlier in the year, there was this other stuff that we really never looked at. What do you think SE stands for? Standard error. So what do you think the standard error of the slope is? Yeah, look. There you go. The slope is that 0.005. So the standard error is that 0.0002 whatever. Got it? And that interpretation was if we repeated this many, many, many times, all the different sample slopes would vary by about that much from the actual population slope. Got it? Yeah.
With standard error of A, you're interpreting that as that just the point, something above.
It would. That's exactly what it would be. But and statisticians use that, but in AP statistics, you don't need to know anything about this. Yeah, you don't need to know anything about like the standard error of A or any of that other stuff. We only focus on slope. Got it? All right, guys, look at that output. What do you think this number is right here? That's like T, like your T. Yeah, not your T star. It's your T value. What do you think this is? Your P value. So if your P value is 0, if we were to do a hypothesis test, are your results significant?
Yes.
Yes. So we'll talk about like what that means later, but everything is do you know what I'm saying? Everything is going to be kind of given to you. Yeah, Nora.
For that S value, is that gonna be how far it on average is varying from the LSR?
LSRL, yeah. In the Y direction. All right, guys, so we have, like I said, we barely have anything left. We're going to go through a confidence interval on a hypothesis test, but this, again, we're getting to like the easiest part. So I'm going to stop here. I know I put book problems up there. On Monday, no, I'm sorry, we won't see you Monday. On Tuesday, we'll finish these notes, like 10, maybe 15 minutes tops, and then you're going to have time to practice. You are going to have a quiz Wednesday, okay?
Short quiz, high quiz.
Short quiz.
I won't be here.